this video, we are going to explain about the project titled Diagnosis of Alzheimer's Disease using Convolutional Neural Network with Select Slices by Landmark on Hippocampus and MRI Images. Introduction. Alzheimer's disease is a progressive neurodegenerative disorder that primarily affects memory, thinking, and behavior. It's the most common cause of dementia and poses a significant global health challenge due to its increasing prevalence impacting millions worldwide. The disease hallmark is the gradual decline in cognitive function, leading to memory loss, impairment in daily activities, and changes in behavior. Within Alzheimer's disease, the hippocampus, a brain structure vital for memory and spatial navigation, is particularly susceptible to damage. Changes in the hippocampus, observed through neuroimaging techniques like MRI scans, serve as a critical biomarker for diagnosing and tracking the progression of Alzheimer's disease. Its atrophy or structural changes often precede cognitive symptoms and are indicative of the disease severity. Previous attempts at using machine learning to classify Alzheimer's disease from MRI images encountered challenges. Utilizing entire MRI image slices for classification resulted in lower accuracy. This was primarily due to the inclusion of irrelevant or non-discriminatory information within the image slices, making it challenging to accurately differentiate between healthy and affected brain regions. The project's main goal is to enhance the accuracy of Alzheimer's disease classification through a more refined approach. Instead of using complete MRI image slices, the project focuses on selectively extracting specific slices containing landmarks on the hippocampus region. By isolating these crucial regions associated with AD pathology, the aim is to improve the accuracy of machine learning-based classification models. The project involves a comparative analysis of different views or orientations, axial, coronal, sagittal, extracted from MRI scans. These specific views, especially focusing on the hippocampus area, are evaluated using advanced neural network models like ResNet-50 and VNet. The aim is to determine which orientations of views, along with which neural network models, yield higher accuracy in identifying and classifying Alzheimer's disease from MRI images. Objective. The primary goal of this project is to enhance the accuracy of Alzheimer's disease classification through the application of machine learning techniques to MRI images. Traditional methods have limitations in accurately identifying affected regions associated with AD pathology. By leveraging machine learning, the aim is to improve diagnostic accuracy for AD using MRI scans. The project aims to investigate and compare different views or orientations of MRI images, axial, coronal, and sagittal, to determine which orientation provides higher accuracy in classifying AD. By analyzing these specific views, the project seeks to identify which perspective or slices of MRI images contain the most discriminative information for successful AD classification. The project introduces a novel approach known as the Select Slices method, focusing on specific slices from MRI images that contain landmarks on the hippocampus region. This method targets key brain regions associated with AD pathology. By isolating these regions and using them as input for machine learning algorithms, the aim is to enhance accuracy by excluding irrelevant features present in entire MRI scans. Two models, ResNet-50 and VNet, are trained using the ADNI dataset for multi-class classification. These models are designed to categorize MRI images into three classes: Alzheimer's disease AD, mild cognitive impairment MCI, and normal control NC. Training involves leveraging these deep learning models to learn patterns and features within select slices of MRI images associated with each class. The project's findings suggest that the Select Slices method, particularly when coupled with the VNet model, exhibits promising potential in improving machine learning performance for AD classification. Through the evaluation and comparison of various approaches and models, the project concludes that focusing on specific regions and leveraging suitable neural network architectures lead to more accurate and reliable classification of Alzheimer's disease from MRI scans. Software and hardware requirements. Hardware requirements of the project are operating system of Windows, processor of Wi-Fi and above, RAM of 8 GB and above, hard disk of 25 GB and above. Software requirements of the project are application is Anaconda, primary language is Python, front-end framework is Flask, back-end framework is Jupyter Notebook, database is SQLite 3, front-end technologies used in the project are HTML, CSS, JavaScript and Bootstrap 4. Working modules or flow of work. To implement this project, we have designed the following modules. The first module is importing the packages. This module involves importing necessary libraries and packages in Python such as NumPy, Pandas, TensorFlow, Keras for implementing the machine learning models and handling data. Exploring the dataset. It encompasses understanding the structure, characteristics, and contents of the dataset. This step includes tasks like examining the dimensions of the dataset, visualizing sample data, identifying features and their types, and understanding the distribution of classes for AD classification. Dataset normalization and shuffling. Normalization standardizes the features of the dataset, ensuring consistency and aiding the model in converging efficiently. Shuffling randomizes the order of the dataset to remove any inherent biases that affect model learning. Splitting the data to train and test. Dividing the dataset into two subsets, the training set and the test set. The training set is used to train the machine learning model, while the test set evaluates its performance and generalizability. Building the model. Creating the structure and architecture of the neural network models. This step involves defining layers, specifying parameters, and configuring the neural network models such as ResNet-50 and LeNet. Training the model. This stage involves feeding the training data to the models to learn patterns and associations between features and labels. The models iteratively optimize the parameters to minimize prediction errors and enhance accuracy. Flask framework with SQLite for sign-up and sign-in. Incorporating the Flask framework for developing a web application, it includes user authentication functionalities using SQLite, enabling users to sign up and sign in to the application. User input and pre-processing. Receiving input from users through the front-end interface. The user input undergoes pre-processing steps such as data cleaning, formatting, or feature extraction required to prepare it for prediction. Trained model is used for prediction. Applying the trained machine learning models such as pre-trained ResNet-50 and LeNet to predict Alzheimer's disease based on processed input data. These models utilize learned patterns to classify or predict AD. Final outcome is displayed through front end, showing the prediction or classification results to the user via the front-end interface, offering insights into the predicted diagnosis or outcome of Alzheimer's disease based on the input data. Algorithms used to implement this project, we have utilized the following algorithms. The first one is pre-trained ResNet-50. ResNet-50 is a type of deep convolutional neural network CNN architecture that contains 50 layers. It's pre-trained on ImageNet, a large-scale image database, and has shown effectiveness in image classification tasks. ResNet-50, being a pre-trained model, is employed in the project for feature extraction from MRI images. The model's convolutional layers learn to extract hierarchical features from the images. These features are then used to train and classify Alzheimer's disease, normal control, and mild cognitive impairment. LeNet. LeNet is one of the early CNN architectures designed by Jan LeCun for handwritten digit recognition. It consists of multiple layers, including convolutional layers with subsampling and fully connected layers. LeNet is utilized as another CNN model for the diagnosis of Alzheimer's disease. Its architecture helps in learning intricate patterns and features within the select slices of MRI images, aiding in the classification of different stages of the disease. As an extension, we applied deep learning model. A dropout layer is introduced to optimize and enhance the model's performance. Dropout is a regularization technique used in neural network to prevent overfitting. It randomly deactivates or drops out a fraction of neurons during training, forcing the network to learn more robust features. Comparison graph. Models are compared with the parameters accuracy, precision, recall, and FN score. This is the accuracy comparison graph. On the x-axis, we have the accuracy score, and on the y-axis, we have the algorithm name. Accuracy is a measure of the overall correctness of a classification model. It calculates the ratio of correctly predicted instances, both true positives and true negatives, to the total number of instances. This is the precision comparison graph. On the x-axis, we have the precision score, and on the y-axis, we have the algorithm name. Precision is a metric that assesses the accuracy of positive predictions made by the model. It calculates the ratio of true positives, correctly predicted positive instances, to the total number of positive predictions, true positives plus false positives. This is the recall comparison graph. On the x-axis, we have the recall score, and on the y-axis, we have the algorithm name. Recall, also known as sensitivity or true positive rate, measures the model's ability to correctly identify all relevant instances in the data set. It calculates the ratio of true positives to the total number of actual positive instances, true positives plus false negatives. This is the FN comparison graph. On the x-axis, we have the FN score, and on the y-axis, we have the algorithm name. FN score is the harmonic mean of precision and recall. It is a balanced measure that considers both false positives and false negatives. It is calculated as 2 times the product of precision and recall divided by the sum of precision and recall. It provides a single metric that balances precision and recall, making it useful when we want to consider both false positives and false negatives in the evaluation. Execution. To execute this project, first we need to open the code folder which contains the project source code files. This is the code folder. This is the dataset folder. In the dataset folder, we are having 3 orientations which we have used in the project, namely axial, coronal, and sagittal. In the axial folder, we have the images for axial, and in the coronal folder, we have the images for coronal. And in the sagittal folder, we have the images for sagittal. Using these images, we have trained the model. This is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. This is the templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, and more, which represent different pages of the website. This is the test images folder, in which we have the test images which we have used during the execution of the project. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. This is notebook.ipynb file. This is a Jupyter notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. This is model file which contains algorithm information which will be loaded into the project code during runtime. This is signup.db file. This file is the database file used to store user information. First, we need to copy the path of the code folder from the address bar of the file explorer. I am copying the path. Open the Anaconda prompt. Use the cd command followed by a space and paste the copied path and hit enter. This command is used to change the current directory to the code folder's path. Compile the app.py file using the command python space app.py. So here I am typing python space app.py and hit enter. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address, which is this localhost, and port, which is this. Now copy this local link provided by the Flask framework. I am copying the link and paste this copied link into any web browser. I usually prefer Google Chrome and hit enter. The homepage of the project is displayed in the browser. This is the front end built using Flash framework. If we are a new user, we need to register first, so click on login. So here we need to enter all these details to register, but I have already registered, so click on sign in now. So here we need to enter the username and the password which we have created and then click on login. We have logged in successfully. So here we need to upload the file to classify the Alzheimer's disease. So click on choose file. Select the image and then click on open. Now click on upload. So here we can see this image is predicted as sagittal NC. Here NC is normal control. Now we will upload some more images and check the Alzheimer's disease. Click on choose file to select the images. I am selecting the fifth image, click on open and click on upload button. So here we can see this image is also predicted as sagittal NC. NC is normal control. Let us upload some more images. Click on upload. So here we can see this image is predicted as coronal MCI. MCI is mild cognitive impairment. Let us upload some more images. So here we can see this image is predicted as axial AD. AD is Alzheimer's disease. So in this way, by uploading the image, we can predict the Alzheimer's disease, normal control and mild cognitive impairment. Click on logout. The conclusion of the project is targeting specific regions of MRI scans, notably the hippocampus, amplifies the accuracy of Alzheimer's disease prediction. By extracting these select slices, the model can disregard irrelevant features present in the entire image, refining its predictive capacity. The method of selecting slices based on landmarks in the hippocampus region outperforms the utilization of entire slices for Alzheimer's disease classification. By pinpointing and extracting these crucial segments, the model gains higher accuracy due to a reduction in irrelevant or non-contributing information. The LeanIt model's simple yet effective architecture has shown considerable effectiveness in classifying MRI images for Alzheimer's disease. Its design facilitates the extraction and analysis of critical features from these select slices, contributing to accurate classification. The project's findings suggest that coronal view of MRI images potentially contains substantial and reliable information crucial for early detection of Alzheimer's disease. The features captured in the coronal view appear to hold significant predictive value, aiding in the identification of the disease at an early stage.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.